Welcome back, Calculus 2 students. In the last video we introduced polar coordinates and the plotting of points. I mentioned in that video that I wanted to look a little bit further at some examples of converting both concrete points and equations. I think I want to put that off and stick with the graphing for this video. And so in My Open Math, if you scroll down to our current block of material and we go to 7.3 to 7.4 polar coordinates, we can see an entire block here for the Desmos graphs and polar coordinates. Now, as I promised, there is a link here to the previous graph that was discussed in the video on plotting points, and so you can manipulate the R and the theta and experiment with some other things as well as you see fit. But today I want to move on to graphing some functions. So let's click on this first one. We'll come back and describe the title in a moment. And what we're looking at here is a function of the form r equals a plus b cosine theta. And so right now I've got a and b both set to 1. And so you should consider this 1 plus cosine theta. R equals 1 plus cosine theta. And so here r is a function of theta. You're thinking of theta as an input value that you're going to plug in and evaluate the expression using that particular value of theta to get the associated value of r. So r is a function of theta, and for each theta there will be a unique value of r. The first thing I want to do here is just hit play on this phi slider. So theta is reserved for the generic variable for equations, whereas if I want particular concrete values I had to change, and I chose to use another Greek letter phi. But what this is going to do is it's going to draw this curve from the angle 0 up to 2 pi, and it'll kind of cycle back again. And so this is just indicating the stopping point of the curve. So I just want to hit play for a moment, and you can see how this is drawn. The value that I see in using this video in the Desmos graph, as opposed to showing you a static picture of a graph, is I'd like you to think about how you would go about drawing the curve, not just what the end result looks like. And I find that a lot of students who are unfamiliar with polar coordinates struggle with this quite a bit, either because they're just plain stuck or because they're mistakenly trying to think in terms of rectangular coordinates. So we're going to play this again in a moment, and we'll also monkey around a little bit with the a and b values. But what I'd like to do is just pause this and come back to the beginning, and let's think about step by step how you would go about plugging in values of theta and evaluating what this function looks like. So again, I want to remind you for this first basic exercise, the a and b values are equal to 1. So where you see a and b above, just think 1 for both of those. And so when I plug in a value of 0, I'm looking at 1 plus 1 cosine 0, 1 plus 1 or 2. And if I start this a little bit, you can see over here, and I'm moving the mouse to hopefully indicate this a little bit, the starting point for our drawing was at the x value of 2. Now why is that? When we graph in polar coordinates, remember from our previous video how we decide a direction and then a distance to emanate from the origin in that direction. Of course, you can allow r to be negative, and so that changes my notion of the how to emanate a certain distance, but let's forget that for a moment. Let's just think about the positive values of r. If I'm looking in the direction of theta equals 0, that's exactly the direction of that positive x-axis. And the radius value associated with that when you plug in 0 is precisely 2. And so I want to go 2 units in that direction. Now let's contrast this for a moment with something like pi over 3. And I'll just try to approximate that here. Okay. Whenever we consider plugging in a pi over 3, you might need to remind yourself that cosine of pi over 3 is 1/2. And so this looks like, in this case, 1 plus 1 times 1/2, which is 1.5. or 3/2. And as you can see, when we head in the direction of pi over 3, we do indeed go out a distance of 1.5. And that is made easier to see by the use of the polar graphing grid as opposed to the Cartesian grid. So each one of these circles that you're seeing, the darker circles, is going to be at an increased radius of 1/2. And you can tell that by looking at the x and y axes. As I go up 1/2, and then 1, and 1.5, and 2. Now, of course, there are lighter concentric circles in between to help gauge smaller increments of distance. But for now, just focus on the darker ones. And notice that if I'm looking at a circle of radius 1/2, by definition, that means that all of those points on that circle are exactly that same radius of 1/2, that same distance of 1/2 from the origin. And so as I proceed in any given direction, in particular pi/3, I can see a distance of 1/2, and then 1, and then 1.5. You may find it helpful whenever you're graphing by hand to draw something like this. It helps if you just mark little tick marks on the x and y axes to get you started, and then you can sketch some rough circles, so that way when you have to look at stranger angles, you can gauge that distance a little bit more easily. Maybe I can, in an office hour with a Zoom meeting, I can demonstrate that on the whiteboard feature. For now, let's get back to this curve. And so we'll notice that whenever we plugged in 0, we had a radius of 2. But when we plugged in pi/3, a different angle, we had a radius of 1.5. And as we plug in new angles, for example, cosine of pi/2 is equal to 0, that should shrink to 1. And as we scroll this a little bit further, this slider, we can see, in fact, that as we point to the direction of pi/2, which is straight up along the positive y-axis, we indeed have that radius of about 1. And so this is the process that we use of plugging in theta values and obtaining r values in order to sketch a graph. Some students may find it helpful to draw a table. I've known other professors to sketch a Cartesian version of the r theta graph, knowing that the cosine gives you some kind of a sinusoidal curve and wave to help approximate. I'm not usually a fan of this process, although I don't necessarily argue against its effectiveness. My concern is that we don't want to spend all of our time translating between coordinate systems in our mind. This is a lot like learning a foreign language. And eventually, if you want to master a foreign language, you need to immerse yourself in it and start thinking directly in that language instead of having to translate from your native language in your head all of the time. And so I'm encouraging every student to start thinking in polar coordinates from the beginning. It might be a little bit of a learning curve and it might be challenging at first, but in the end it's going to have a big payoff. You want to be able to learn to think in polar coordinates and not translate from Cartesian coordinates all of the time. So as we scroll this curve and plug in different values, we can see this behavior where it comes back to the origin. Now, where does it do that? So look at how the curve, how it sort of asymptotically curves in around this value right here. Okay? And actually it may be a little closer to 5 pi/6. If we zoom in a little bit, we probably can see that a little bit better. So let's try it. Okay. Nope, it's not at all. It's crossing over, and I think if we zoom in, we're going to see that it even crosses over that smaller angle. And it does. So it seems to be flattening out a little bit and asymptotically approaching this horizontal line. What does that mean? So let's zoom out a little bit so we can see the full picture once again. So when does this get back to 0? Well, if I look at this equation and ask what value of theta is going to give me an r value of 0, either by solving algebraically or a little bit of guess and check, I can figure out that when theta is equal to pi, cosine of pi is -1, and therefore this looks like 1 plus -1 or 0. And so when we get to the angle pi, as we rotate, we should be seeing that r value shrink to 0, and that is in fact what happens. Okay, so now that we understand how this works, plug in your thetas, get your R. You can start to envision what's going to happen by considering different values of theta and the corresponding values of R. Now when we get back to 2 pi, cosine of 0 and cosine of 2 pi are identical, and consequently the value of R is going to be identical as well. And so we end up back to where we started. And if we continued past 2 pi, we would retrace the curve. If we went to negative values of theta, we would be tracing the curve backwards. Okay. Now as we change the values of A and B, we're going to see some various changes in the graph as well. Okay, so A, as we enlarge it, and let's actually zoom out of our picture a little bit. As we enlarge A, okay, we see a change in the shape a little bit. Now all of these graphs are called cardioids, and I think I've got that labeled on the link to this video. You can have a look at that later and verify that I'm correct in that. But all of these are called cardioids because of this general heart shape. And so if I shrink A down, you can see that sort of rounded, more not like a drawing of a heart, more like a closer to a human heart shape. So these are called cardioids. Now as I shrink A down, smaller than 1, I can see a loop form. And what's going on there is that at a certain point of value of theta, we actually end up with negative values of R. So for example, when A is 1/2, what happens is that the cosine value is larger in magnitude than 1/2, but it happens to be negative. So for example, whenever it is equal to cosine is equal to negative radical 3 over 2, well, when you add the 1/2, that's going to remain negative and give you a negative R value. And so the R is going to reach 0 a little bit sooner than we had previously discussed, and then turn negative. And so for some of these values just shy of pi, you may see negative values of R, and you're pointing in the opposite direction. Let's go ahead and hit play on this from the beginning and watch it draw like a little bit of an animation in front of us. And so once again, I encourage you to plug in particular values of A and B, and you could start with A equal 1/2 and B equal 1, and generate the R values for yourself and see what happens. In particular, note whenever R is equal to 0. Okay, now if I pause that for a moment and I change the value of B, you can see that that will likewise have a change in the shape. And what's happening here is the relative comparison of A to B is going to be what's at play. And so when you increase both A and B, you'll see a similar shape to what we saw before. And so if I have them both doubled, and I zoom out so you can see it, that's a lot like the shape that we started with when A and B were both equal to 1. But when A is drastically larger than B, we see that flatten out on the left-hand side. Whenever A is smaller than B, we see that loop appear. When A is negative, okay, we see a little bit different behavior, and when B is negative, we see a little bit different behavior as well. Okay, so anyway, the link is on My Open Math. I'm going to stop this video so that I can keep these reasonably short. This was already stretched to 14 minutes. Probably my future videos will have a little bit less of the exposition and more just the short demonstration. But given this was your first exposure to the sketching of the curve, I wanted to make sure I provided a few extra details. Do make sure that you play with the slider and the values and experiment. I would encourage you to also handwrite some computations just to make sure you understand what's going on, and to hand draw the graphs. Do not rely on the online graphing calculator to acquire your understanding alone, because during an exam you will not necessarily have that option. All of this stuff is going to be used quite frequently in your Calculus 3 course, where we're going to do some multiple integrals. So you want to make sure you learn it well. All right, until next time.